So today, what we're going to be talking about is how to take an antiderivative of something that's a little more complex than what we've been dealing with before. Okay, and the best place to start with this is to actually go back and talking about taking the derivative of a function using the chain rule. So let's just say we had something like sine of 3x squared, okay, and we want to take the derivative of sine of 3x squared. So we're going to try to take the derivative of sine of 3x squared. But I'm going to put this stipulation on you. I'm not going to let you use all of the kind of shortcuts that we did with the chain rule. I'm going to make you actually use a u substitution, because what we're going to be doing today is going to be an antiderivative with u substitution. So I want to think back to how you would work a u substitution with the chain rule and then kind of relate that to an antiderivative with a u substitution and see how that plays out. Okay, so if we were going to do a u substitution whenever we're trying to take the derivative using a chain rule, what do we always pick as our u? The inside. Okay, that's exactly right. And what is the inside of this function right here? Okay, so u will equal 3x squared for us. Okay, so let me just make sure I get my notation up here. We're trying to take the derivative of sine of 3x squared using the chain rule, but we're going to do a u substitution. So we're saying that u is going to equal 3x squared. So now we're trying to take the derivative with respect to x of sine of u. Okay, so we're just trading out that u. So we trade out the 3x squared for the u, and now this is what we have. And what's the derivative of sine? Now we're just really simple. It's just what? Cosine of u. But I want to make sure that we're clear about this. So think with me now about implicit differentiation, right? We're trying to take a derivative with respect to x, but what is our actual variable in the problem? U. So what do we have to do according to implicit differentiation whenever our variables don't match like that? Okay, so du dx. Okay, so now we have to multiply by the derivative of u with respect to x. So what I'm going to do is I'm going to come back up here to my u, and I'm going to see if I can find the derivative of u with respect to x. And I can, because this function u is written in terms of the variable x. Right? So we can get a derivative here. What's the derivative of 3x squared? 6x. And now what I'm going to do is I'm going to use this information over here, okay, those two things, and I'm just going to plug them in respectively. Put that in there and put u back in. So this is the cosine of 3x squared times 6x. So it's the cosine of 3x squared times 6x. So hopefully you can see what's happening here is that whenever we have a chain rule, remember the big idea by the chain rule is that we always end up multiplying by the derivative of the inside, okay? So we multiply by the derivative of the inside again and again and again. So if we ever get to an antiderivative where it seems like there are lots of different things being multiplied together, then the odds are that in the original function, okay, before a derivative was taken, if you want to think of it that way, before a derivative was taken, it had to be, you know, some compact function that then got really long because of the chain rule. So when we see things being multiplied together, that will be the case. So now let's actually try to work this thing backwards. Let's say that we're going to take the integral of cosine of 3x squared times 6x with respect to x. Okay, so we're going to try to take this antiderivative. And notice all I'm using is this function right here. So does anybody know what the answer is already? Yeah, sine of 3x squared, okay, because we're just going back now from what we did before. But I just want to point out to you some of the things that we're trying to do in order to accomplish that, okay? Just look and notice that this is, you know, two things being multiplied together. It's this cosine function times this 6x right here. And what a u substitution is going to allow us to do whenever we're trying to take an antiderivative is to try to target what is extra in a problem and what is there kind of at the base or at the root of a problem. Okay, that's kind of the way I want you to think about it. Because remember, when we have a chain rule, we continually multiply by the derivative of the inside times the derivative of the inside times the derivative of the inside. And what we get is this big, long function with all of these things being multiplied together, okay? Multiple things being multiplied together. And so what we want to do is we want to try to be able to figure out what is extra stuff that's just kind of been multiplied, added on and on and on because of the chain rule, and what was there kind of all along, if that makes sense to you, okay? And so what we're going to do is we're going to try to pick a u in order to help us out with that. So we're going to try to sub something out for a u. We're going to use a u substitution. And so what we're trying to identify is what is extra stuff that came along by, the chain rule, and what is the stuff that is kind of really substantial in the problem. So how do we usually choose a u whenever we're dealing with the chain rule? You look for something on the inside, and in this case, what's on the inside? 3x squared. Okay, so what we're doing when we look at that is when you see that 3x squared on the inside, then that stuff was there to start with. Because remember, with the chain rule, what do you always do with the inside? You leave it alone whenever you're putting something in, right? And then you multiply by its derivative. So what we want to do is we want to check and see what extra stuff came from taking the derivative of the inside. So the u is the inside. So if we take the derivative of u with respect to x, we can figure out what extra stuff just came from, multiplying by that thing with the chain rule. So this right here would be what if we take the derivative? 6x is what we get. So what that tells me is that this 6x back here actually just came about from the chain rule, right? That's where it came from. So what we want to do is we kind of want to get rid of it, to be completely honest with you, okay? So we'll get to that in just a second, but here's what I want to do now. I just want to go ahead and rewrite this integral as the cosine of u times 6x dx. And I want us to pay attention to our notation here and just how we're going to use the notation in order to help us work some of this out. Okay, so this u right here, so if you look at what we have the cosine of u times 6x, and we're trying to take the antiderivative with respect to x because of that dx right there, right? Well, that's a problem, right? Why is that a problem? Yeah, we have a u in the cosine, and then we have an x back here. So we have separate variables, right? We have two different variables here. So if this cosine is now defined in terms of u, what do you think we want to take the antiderivative with respect to? U. So we don't want this to be a dx anymore, so that we're not taking the antiderivative with respect to x. We really want it to turn into a du. Okay, so I just want to draw your attention back over here. And notice that here we have a what? A du. So what I'm going to do is I'm going to try to isolate, okay, I want to be able to substitute in for this dx over here, right? I want to trade that dx out for something that has a du. So I'm going to come to this derivative that we took over here, and I'm going to solve for dx so that I can then trade it out. Okay, so watch what happens. So I'm going to multiply by dx on both sides of this equation right here, and those two cancel. And we get that du is equal to 6x times dx. And now I'm going to divide by 6x on both sides. So these cancel. And we get that du over 6x is equal to the change in x. So I'm going to use that and plug it in. So now what I'm looking at is the integral of cosine of u times 6x times, and for dx, I'm plugging this stuff right here in, du over 6x. Now if you notice, what's going to happen with my 6x's now? Yeah, they're going to cancel out. Those 6x's cancel. And so once I've canceled them, because that 6x was just extra that came along with the chain rule, right? It wasn't actually part of my base function in the original. It was just stuff that got added on due to the chain rule. And so now I can get rid of it and kind of just see what was there from the beginning. And so now I can get rid of that 6x And we're looking at the base of this whole thing being cosine of u. And so now my antiderivative is just cosine of u du. Well, the antiderivative of cosine of u with respect to u, what would that be? Sine of u plus c, right? We can't forget our constant on these because they're indefinite. And now I'm going to go back and I'm going to take my u, which was 3x squared. And so I'm just going to plug in for u down here. This is sine of 3x squared plus c. And we already knew that that was the answer, right? But that's how we're getting it. And then what the u substitution is going to allow you to do, like I said, is cancel out some of the extra stuff that came along because of the chain rule, be able to get down to, like, you know, the bare bones, what was really essential in the problem, and be able to take an antiderivative from there, okay? So it'll really help you whenever you're dealing with stuff like that. So let's look at another example. I'm just going to work a few examples together. And you'll have to get good at choosing a u, okay? That'll be like the hardest part of these problems, is choosing a good u. But the farther along you go in it, the better you'll get at it. Okay, so let's do this one now. X times x squared plus 9 to the 5th. Okay, so does anybody know what you would want to pick for u here? Yeah, x squared plus 9 is exactly right. There's a couple of different things you want to look for, okay? You want to look for something that's on the inside of something else, right? So since that x squared plus 9 is inside of the 5th power, that's a good indicator for you that you want to use it. But you also want, you know, because of the chain rule, you always multiply by the derivative of the inside, right? Okay, so you also should see outside of that thing, so outside of this piece right here, you should see the derivative of the inside. Well, what's the derivative of this inside piece right here? The 2x. Well, look what you have right out front right there. You have an x. Now, the fact that the 2 is not there, I just want to go ahead and point this out right now. The fact that the 2 is not there is completely meaningless, okay? Because whenever we start working through this process, do we really need the 2 to cancel out? No. Whenever we get to the end, if you remember where we started subbing in the last problem, where we really needed stuff to go away was the x values, right? We didn't need a cosine u 6x du, right? We don't need an extra x in there whenever we're going to be trying to take the antiderivative with respect to u. So what we really care about is this x canceling out, and the 2x is sufficient to be able to do that. And that'll start making more sense to you kind of as we go along, okay? So the first thing I'm going to do is come over here and go ahead and get du dx, which is, 2x as we just said. And then I need to get dx alone, so I'm going to multiply by dx on both sides, and so du is equal to 2x dx. And then I'm going to divide by 2x on both sides, so that dx is equal to du over 2x. So we're dealing with the integral of x times, now what's x squared plus 9? U. So u to the 5th, right? I'm subbing in for u. Yeah, so du over 2x. And here I have an x on top and an x on bottom. Okay, so my x's cancel out. But what do I do with this 2 down here? Yeah, it's on bottom, right? So since the 2's on bottom, it really operates more like a 1/2. And does everybody remember our property of integrals, that if we have a constant, what can you do with the constant? You can move it all the way to the front. So this is the same thing as 1/2 of u to the 5th du, right? So that constant down there, that's a 2. Since it's on bottom of a fraction, it's a 1/2, okay? And I always pull my constants out like that. It just makes this thing so much easier to look at when that 2 comes out, right? This thing just kind of makes more sense to me whenever I pull that 2 out. And so I need 1/2 of, and now I'm ready to take my antiderivative. What's the antiderivative of u to the 5th? 1 over 6 u to the 6th plus c. And I'm keeping that in parentheses because what do I need to do with this 1/2? Yeah, I need to distribute that 1/2 right there. So what is 1/2 times 1/6? 1 over 12 u to the 6th plus, what happens when you do 1/2 times a constant? Yeah, a constant times a constant creates a constant, right? It may be it's a different constant, so if you want to call this one C1 and this one C2, it's still a constant though, okay? It doesn't change the fact that it's a constant. And now we need to plug in for u. U was x squared plus 9. So this is 1/12 times x squared plus 9 to the 6th power plus c. That's what they started with. Yeah, on an FRQ, if you forget plus c, it will hurt you. Yeah. There's usually a separate point for the antiderivative and the plus c. So if you put the antiderivative and you remember to put plus c, you get 2 points. But if you just get the antiderivative right and forget plus c, you only get 1 point. Or if you blow the antiderivative but you write plus c, you get 1 point. Okay? So it's a great way to pick up an extra point on a FRQ where you know you're supposed to take an antiderivative but you have no clue how to take that antiderivative. Just make up some, gibberish and then put a plus c at the back and get your point for the plus c and keep moving. Okay? All right, here's another example. Okay. We got x squared plus 2x over x cubed plus 3x squared plus 12 all to the 6th power. Why would you choose the bottom one as u, Marshall? Yeah, because it's inside of the 6th power, right? Okay, so it's inside of the 6th power. So that's a fair enough reason for me to just go ahead and say, all right, I'm going to choose that as u then. So x cubed plus 3x squared plus 12. And now our hopes are that the stuff on top will end up doing what? Canceling out. Okay, yeah, so we hope that that x squared plus 2x on top will cancel out for us. So let's do du dx. So what's the derivative of this thing going to be? Plus 6x. Okay, so that's if we were right and we said, hey, I think that thing right there was on the inside. I think that x cubed plus 3x squared plus 12 was on the inside of a chain rule problem. If that's true, then the derivative of the inside should exist somewhere within the problem. Does that make sense? And so we're hoping that we can find it and eliminate it to get down to kind of the root of the problem. So this right here is what we're saying the derivative should be. So I'm going to multiply by dx on both sides, and now my 3x squared plus 6x is going to have to go in parentheses, right, because I would need to distribute that change in x. And then I'll divide it back across. So my change in x is going to end up being du over 3x squared plus 6x, right? Because all I'm going to do is divide that 3x squared plus 6x back across. And maybe you've started to pick up a pattern that what happens, yeah, du ends up being over the top of your derivative. Now that's not airtight. It doesn't happen that way all the time. But in general, that's what you'll see, something like that. Okay, so now if I plug stuff back in, then that stuff up top just stays, x squared plus 2x. I didn't do anything to it. But now on bottom, what do we have? Very good. U to the 6th. And then for dx, we're subbing this stuff, which is equal to dx, in. So it will be du over 3x squared plus 6x. And now our hopes were that that stuff on top would cancel out, but it doesn't look like that's happening right now. So what could I do to make that happen? Yeah, take this thing on bottom over here, and let's factor out a 3. So this would be x squared plus 2x over u to the 6th times the change in u over, and now here we're going to factor out our 3. So if I pull out that 3, then I'm going to get x squared plus 2x. And that's exactly what we were hoping for, because now these things are being multiplied together, and I have an x squared plus 2x on top and x squared plus 2x on bottom, and so those two things will cancel. What am I going to do with this 3 down here on bottom? Bring it out as what? Yeah, since the 3's on bottom, I'm going to bring it out as a 1/3. Okay, so this is 1/3. And now I have 1 over u to the 6th du. Okay? So 1/3 times 1 over u to the 6th du. Now, how would you take the antiderivative of this? Take that u to the 6th and do what with it? Move it up. Yeah. So this is 1/3 times the integral of u to the -6 du. So 1/3 times, what's the antiderivative of u to the -6? Right. U to the -5th, and then you got to multiply by the reciprocal, which would be -1/5, right? So -1/5 times u to the -5th. And now we need to distribute this 1/3. Okay, so what's 1/3 times -1/5? Yeah, top times top and bottom times bottom, so -1 over 15, u to the -5th plus c. Yeah, make sure you're adding 1 to that exponent, not subtracting, right? So the -6 plus 1 makes -5. Okay, and now we want to plug back in for u, which was x cubed plus 3x squared plus 12x. So down here, I'm just going to trade that back in for my u. So x cubed plus 3x squared plus 12 to the -5th plus our constant of integration. All right, the next one is a fairly easy one. Sine of 7 theta plus 5. Okay, so we want the antiderivative of sine of 7 theta plus 5 d theta. Yeah, hopefully u is fairly easy to pick in this one. What's it going to be? Yeah, u is going to be 7 theta plus 5. So now when we take the derivative, it's going to be the derivative of u with respect to what? Good. With respect to theta is 7. Yeah, it's just 7. Okay. So you always want to take the derivative of your u and figure out what should have been there by, taking the derivative of the inside with the chain rule. Yeah, so change in theta is equal to the change in u over 7. Very good. So d theta is equal to du over 7. So this is sine of u times what? Over 7. What do you think I'm going to do with that 7? Okay, I'm going to bring it out front as a 1/7. That's exactly right. So this is sine of u du. And what's the antiderivative of sine? Okay, so I have 1/7 times negative cosine of u plus c. So I'm going to distribute that negative 1/7 now, that positive 1/7. And so negative 1/7 times, positive 1/7 times negative cosine makes negative 1/7 cosine. And I'm going to go ahead and plug in for my u. My u was 7 theta plus, what was it? Yeah, 7 theta plus 5. So I'm going to go ahead and trade that in for u. 7 theta plus 5 plus my constant, because 1/7 times a constant, remember, will just make another constant. Okay, so it's not going to change the fact that we're dealing with a constant there. And this makes perfect sense because if you looked at this right here and you think that it's the derivative of this has already been taken using the chain rule, if you took the derivative of something like that using the chain rule, what would you expect to be out front? You would expect a 7 to be out there because of the derivative of the inside. But there's not one in this case. So the logical explanation for why that 7 is not there anymore would be that there was a what? A 1/7 out front to cancel it out as soon as you multiplied by it with the chain rule. And so that's how we know, well, we need a negative. It's going to be, the cosine because of the sine. So, yeah, there you go. Exactly. So you can see that negative 1/7 is going to be out front to cancel that 7 as soon as we multiply by it with the chain rule. Okay? So that's what ends up happening there. All right, let's look at one like this. Okay, so picking a U may be a little bit, little more difficult with one of these. Good. I'm glad you remember that because whenever we do the chain rule, I always say that whenever we have one of these, the inside is actually the power, it's the top, the exponent. Okay, so U is negative 9t. Okay. If we were doing this with a chain rule, what would you expect to be out front right here? A negative 9, but it's not there, so what must have been there to cancel it out? A 1/9 of some sort. So let's see what we get. Well, let's take the derivative with respect to t, and what do you get? Negative 9. So, very good. Okay, the change in t is equal to the change in u divided by negative 9. And so now we have e to the u times du over negative 9. Okay, and you guys are right. We're going to pull this negative 9 out, but it's on bottom, so when it comes out as a negative 1/9. Yeah, so negative 1 over 9 e to the u du. Because it's still negative because whenever we plugged it in, it stayed negative the whole time, Kat. And if we don't have a way to cancel out the negative, then it has to stay that way. Okay? So the negative didn't cancel. It was a negative in here, so when I pull it out, I'm pulling it out as a negative. Okay? Okay. Since it's a constant and it's being multiplied, if you think about area under the curve, right? Okay, so if you take this function right here, I'm just gonna make a function like that, okay? And if you have something like this right here, this would be e to the u divided by negative 9, okay? It's gonna take every one of these e to the u's and do what with it? Divided by negative 9. So in essence, what it's gonna do is if you divide something by negative 9, it's gonna make it 1/9 that height, right? Okay, so if this is e to the u divided by 9, okay, and I'm just going to use positive numbers here, okay? If that's how tall it is, then how would you compare just e to the u? Okay, if we had just the function e to the u, what would you say about it compared to e to the u divided by 9? It's 9 times higher, right? Every single height is 9 times higher. So when you think about an integral being the area, right? If we wanted to, if this is the one that we want, okay, but I actually told you about e to the u, and we wanted the area from here to here of e to the u, but I could give you the area, we want the area of e to the u over 9, right, Matt? But I can give you the area of e to the u. Well, since every single one of these heights has been, they're 9 times taller, then the way you could get the area would be to take the total area and do what with it? Divide it by 9, because if you divide it by 9, that total area is going to be, since every spot has, if you think about it as a rectangle, right? If this rectangle is 9 times taller than the other one, what's going to happen to the area when you do, whenever you multiply length times width? The area is going to end up being 9 times larger, right? So since this one's 9 times taller, the area is going to be 9 times larger. So e to the u now, so this e to the u right here is now 9 times taller than e to the u over 9. So what we could do is so instead of doing e to the u divided by 9 every time, we could just do e to the u, but then what are we actually going to do to that area in the end because of this 1/9 out here? We're going to divide it by 9 later. Instead of dividing every one of the heights by 9, we'll just get the final area and then divide that by 9. So it works the same way. And then if you wanted to make something taller, you could just find the area and then multiply later on instead. Okay? So it has to do with the effect that it has with area underneath the curve. Okay? So that's why that works the way it does. So now if we have -1/9, and then what's the antiderivative of e to the u? E to the u plus c. So -1/9 e to the u. Yeah, and we're just going to plug back in. That's right. So e to the u is 9t. Or sorry, u is -9t. So we plug in plus our constant. And there is our antiderivative. All right, so here's another one. Tangent theta d theta. Where did what come from? Yeah, the t right here. I plugged back in for u. This was 9. It was in t. It was in terms of t all along. It just wasn't an x. Yeah, so get the t back. Okay, so look at this one. Tangent of theta d theta. Now, this one in and of itself, right, this one in and of itself looks fairly simple. It's like there's no u substitution to really be done, okay? But what's the antiderivative of tangent? Yeah, we don't know. So this is actually much more complicated than it looks. There's not a really simple antiderivative for tangent. So what are we going to do to this tangent? Change it into sine, very good, over cosine. Yeah, change it into sine over cosine. So now that it's sine over cosine, we can try to pick a u. Okay, so yeah, that's difficult, right? Because there's not one on the inside. That's usually a good clue. There's like if it's on the inside of a squared or something like that, that's the one we want to pick. So there's not one on the inside here. And at the same time, the other clue we look for is we want to see the function and its derivative, right? Well, what's the derivative of sine? Cosine. And what's the derivative of cosine? Negative sine. So they both have their derivative there. So which one do we pick? Well, here's a little clue. The bottom, okay? You want to choose the bottom because that's going to allow you to use a natural log in the end if you pick the bottom. Now, you're more than welcome to pick the top, okay? So what's going to happen, though, is if you pick the top, you're going to go through this whole thing and you're going to get to a point where you get stuck. And if that ever happens on one of these problems, you're working through and then all of a sudden you get somewhere where you are just completely stuck. 9 times out of 10, your issue is you picked a bad u. Okay? If you pick the wrong u, if you pick a bad u, you will get stuck. Okay? So, if we picked sine, I could take you through the whole process right now and just let you get stuck and be like, see, you picked the wrong u, and then go back and tell you. But from the beginning, let's go ahead and pick cosine. It's on the bottom, so that's helpful. So we'll let u equal cosine. So the change in u with respect to theta is going to be what? Negative sine of theta. So the change in theta will be equal to the change in u divided by negative sine theta. So this right here is sine of theta over u, because cosine was our u, times the change in u divided by negative sine theta. So my sines cancel. Okay, my sines cancel. What am I going to do with this negative sign right here? Yeah, I'm going to pull it out to the front as a -1. You know, it's still a constant. So negative times the integral of 1 over u du. And this is an easy antiderivative. What's the antiderivative of 1 over u? So negative of And then the antiderivative is natural log of u plus c. Okay? So I'm going to distribute that negative, and it's negative natural log of, and I'm going to go ahead and plug in for u. U was cosine theta plus c. You could call it minus c. That would be perfectly fine. But what if c is a positive number? Well, then, all it's going to do is just kind of change the way it looks. Yeah. So if c was a negative, then you'd be like, oh, it's going to be a positive. If c is a positive, it's going to be a negative. You can manipulate c to be whatever you want it to be, okay? Just based off of the way that you write it within the context of the problem.
So if you took the derivative of that, you'd get...
Yeah. If we took that derivative, we would get back to tangent. Okay, so let's look at this one. We'll do x squared, the square root of x cubed plus 1 dx. All right, what's my u? U is x cubed plus 1. It's on the inside, right? That's a good clue. So du dx is what? 3x squared. So dx is equal to du over 3x squared. So we have x squared times the square root of u times du over 3x squared. All right, yeah, I'm going to cancel my x squareds. And then the 3 is still there, so I'm going to pull the 3 out as a 1/3 since it was on bottom. And I'm going to go ahead and call this u to the 1/2 power, right? Because the square root is the same thing as a 1/2 power. And so I have 1/3 times, and this is going to be u to the 3/2, right? I'm going to add 1 to the power. It's going to be the 3/2. And then I also need to multiply by the reciprocal, so it's going to be 2 over 3. Plus my c, right? So when I distribute the 1/3, I get 2 over 9. I'm going to go ahead and plug in for u. What was u? X cubed plus 1. So x cubed plus 1 to the 3/2 power plus c. Okay, so here's one with trig functions. So tangent cubed theta times secant squared theta d theta. Not all of them. Yeah, what would you pick for u? Why would you pick tangent, Kat? Yeah, you want something on the inside. So that tangent is actually on the inside of a cubed, right? Because it's tangent cubed. So you need to think of it like this: tangent of theta cubed. So it's on the inside. And but so is the secant, right? They're both on the inside. But the only difference is if you make this your u, what's the derivative of secant? Secant tangent, right? So if you make this your u, then do you have a secant tangent? No. But what's the derivative of tangent? Okay, so if you make this your u, is the derivative of it still there? Yes, secant squared is right there next to it. Okay, so if you make the tangent your u, then you'll have everything you need there. I'm going to back this out. Okay, so u is going to be tangent theta. So du d theta will be equal to secant squared theta. Very good. D theta is going to equal du over secant squared theta. So this tangent is now our u, so this is u to the third power times secant squared theta times du over secant squared theta. Our secant squareds cancel, and we get u to the third du. Yeah, and I'm glad you said that because they should always be simple. You know, if you pick a good u substitution, when you get down to the end, it should actually be a pretty simple problem every time. So, say that again. I know, and I've done it that way in the past, like where you just call it that, and you say like with the chain rule you would do this, you know, du d theta is there, so you just take the antiderivative of that. But actually, I've found that students find that more confusing than what we're doing right now, and getting it down to just this instead of the extra stuff, and you seeing that the chain rule is actually incorporated in there already. When you just get it to this and things have been eliminated, they just see it a lot easier. Stuff. It's either way. Yeah. Okay, so the antiderivative of this is going to be what? Yeah, 1/4 u to the fourth plus c. So this is 1/4 times tangent to the fourth plus c. So 1/4 tangent theta to the fourth plus c. All right, so here's another one. This is what I got right here. Yeah, there's the final. All right, so here's another one. X over x squared plus 1. Yeah, the bottom is a good choice. There's nothing inside of anything else in this one, right? But the bottom is a good choice simply because what's the derivative of x squared? 2x, and there's an x up top, right? So we feel like we could get that to cancel out. So we'll choose the bottom as u. So du dx is equal to what? Yeah, 2x. So x over u times du over 2x whenever we sub things in, right? These x's cancel. And so I'm going to pull that 2 out as a 1/2. So 1/2 times the integral of 1 over u du. So that's 1/2 times, and what's this? The integral of 1 over u du? Natural log of u plus c. So 1/2 natural log of x squared plus 1 plus our constant. Yeah. Okay, so I'm going to do 2 more with you, and these 2, one of them is going to be a long one, okay? And then one of them is going to be a just another trick that I want to show you, okay? So I'm going to do 2 more with you, and then we'll be finished. But one of them's long, and one of them's a trick, okay? So we'll do the long one first. All right, so I'm gonna so the inside of sine my u. So what's on the inside of sine? Okay, so let u equal 3x squared. This is exactly what I was hoping you would do. Okay. So this, don't worry, it's okay. You will get the correct answer. I'm not going to take you down a trail where you can't get a correct answer. You can still get the correct answer. All right, hang on. Let's work the problem. So du dx is equal to 6x. So dx is equal to du over 6x. So this is 3x times the sine of u times the cosine squared of u du over 6x. This, so those x's will cancel, right? The 3x on the top and the 6x on the bottom. So the x's in both of those cancel. But now notice that we have a 3, put all that stuff over 1 and look, there's a 3 on top here and there's a 6 on bottom. So the x's are gone. So if I pull out the 3 over 6, I can just go ahead and call that 1/2 sine u cosine squared u du. Okay. What's the antiderivative of that? Well, there are two things that are still being multiplied together, which leads me to believe that the chain rule was used yet again, right? So now I need to pick another u, also known as a W. That is exactly right, okay? So, all right, so what would you pick as your W this time? Very good. Cosine, because it's on the inside of the squared, and you see its derivative there. So cosine of u, right? It was cosine of u that we're picking to be our W. Because you just want the inside. You don't want the whole thing, okay? So the change in W with respect to u would be what? Negative sine u, okay? So du is going to equal dw over negative sine u. And notice now my goal is to not get everything in terms of u, but to get everything in terms of w. So this is, I'm going to come back to my integral. It's 1/2 times the sine of u. And now cosine u I've changed into w, right? So this is w squared. And then I'm going to sub this stuff in for du. So it's dw over negative sine u. And my sine on bottom and my sine on top cancel. The negative that's left over, I'm going to pull out front and make it negative 1/2 times, or sorry, negative 1/2 times the integral of w squared dw. So this is negative 1/2 times, and what's the antiderivative of w squared? One-third w to the third plus c. And now I'm going to distribute in my negative 1/2. So it's negative 1 over 6 w cubed plus c. Okay, so my w is cosine u, so this is negative 1/6 cosine cubed of u plus c. Very good. And then we also need, so w is cosine of u, but then u, if you remember, is 3x squared. So I'm going to come back, and now where I have this u, I'm going to change it to 3x squared. So there's my final answer. Yeah, the sign in the beginning was just part of the chain rule. It was extra, and that's why we needed to get rid of it, okay? Because it was just something that was created through the chain rule. Okay, so Cece actually said something that I wanna point out. Okay, what did you say about the u that we had? Okay, the u that we picked wasn't wrong necessarily, but you used a different word. You said that we should pick a better u. That's exactly right. There is such thing as a better u than some u's are better than others. Not all u's are created equal. So I'm going to go back up here. I'm going to go back up here. And now let's pick a different u. Cece, what u were you saying we should pick? Cosine of 3x squared. Because it's on the inside of the squared, right? And we also want to see its derivative there. Well, what is the derivative of cosine 3x squared? 3x squared times 6x. That's exactly right. And so now dx is equal to du over negative sine of 3x squared times 6x. So we're going 3x times the sine of 3x squared. And now cosine of 3x squared is my u, so this is just u squared. Du over negative sine of 3x squared times 6x. And if we pick the right u, we can get all of these to cancel out in one instead of having to go through multiple steps, right? Because now, because we picked a better u, the sine of 3x squared cancels out, and my x's cancel out all in one step. And now on bottom I have a negative 6 and this 3 on top, so I can go ahead and pull out a negative 1/2 because it was 3 over 6 u squared du. Thank you, negative 1/2 u squared du. So now it's negative 1/2 times 1/3 u cubed plus c. So that is 1/6, negative 1/6. U is here. It's already really straightforward. It's cosine of 3x squared, that should be cubed, plus our constant. And so we get there in half the time, right? Instead of having to do multiple substitutions, we can just do one and then finish, okay? That's just coincidence. Yeah, don't let that fuel your decision-making process, okay? All right, so one last one, and this is the trick, okay? So this is a trick that I'm going to... Okay, so this one right here is going to be a little tricky compared to the other ones that we've done, okay? X times 5x plus 1. What would you want to choose as u right here? Okay, that is perfectly legitimate to want to choose 5x plus 1. And you do want to choose 5x plus 1. That actually is the proper u for you to choose. The only problem is that this isn't going to work out as nicely as other u substitution. This is not going to work out as nicely as other u substitution problems. Because when I take the derivative of this, which I do want to take the derivative of this, du dx is going to be what? 5. So dx is going to equal du over 5. And say what you said again, Landon. Yeah, what I have right here is not sufficient to get rid of that x on the outside. If you've noticed, every time we've picked a u substitution in a problem like this, we know we're going to take the derivative of u. And so what happens to the exponent whenever we take a derivative? It drops by 1. And so since this is now 2x, it'll let us get rid of that x. But the exponent in the u that we choose is typically 1 degree higher than the exponent on the outside, so that when we take a derivative, they will match in degree, right? Because the degree is going to drop 1 when we take a derivative, and then they'll cancel one another out. So you see it here, this x squared is 1 higher than this x. Okay, and then there's other problems. Let me find it. Here again, we see on the inside there was an x cubed, and on the outside there's an x squared, so that when you take the derivative and it drops by 1 degree, it'll be able to cancel out. And I don't know if I have another example with one like that we've covered today. Nonetheless, there may be one here. Yeah, these were x cubed and x squared, so that they could cancel out x squared and x. They're going to drop by 1 degree. Does that make sense? Okay, so the issue that we're running into on this one is the fact that the degree of the exponent inside of the square root and on the outside are equal to one another. Okay, so that's a problem. So here's what I'm going to do. I'm going to say that this right here is x times the square root of u, and then we have du over 5. Okay? And when I get to that point, I'm noticing that this 5 will not cancel out that x, right? It's not going to cancel. So I have a real problem here because my variables don't match. You know, I have an x, a u, and I'm trying to take the integral with respect to u. So what could I do to fix this? Well, look at what I have. I have a u and a u and an x. What would be the best thing that could happen? Yeah, this x right here, we could change it into a u. Because what if we change this x into a u? Then we'll have nothing but what? U's. Now, do we know anything about a relationship between x and u? Yeah, this is our relationship between x's and u's, right? So this is what we know about x and u, okay? So what I'm going to do is I'm going to get x by itself. And if I can get x by itself, it will be described in terms of u, and then I can plug it in. So I'm just going to take that and I'm going to subtract 1 from both sides, and that'll give me u minus 1 is equal to 5x. And then if I divide by 5 on both sides, that means u minus 1 divided by 5 is equal to x. And I'm going to take that and plug it in there, and then this is going to be math magic, right? So there's u minus 1 over 5 times the square root of u times the change in u over 5. And now everything I have up here is in terms of u. I have nothing but u's. So it was a really nice way to get rid of that x so that I can now try to take a derivative. Okay, so let me put this over 1, and I'm just going to try to simplify things a little bit. So if I put that, square root of u over 1, I have 3 fractions multiplied together. So on bottom, I have 5 times 1 times 5, which makes 25. And since that's a constant, I'm just going to rip it out and put it in the front. So 1 over 25 times the integral of u minus 1 is being multiplied by the square root of u times the change in u. And now, because of the way that this thing right here is set up, what I can do is this square root of u on the back right here is actually a u to what power? 1/2. Okay, so I want to distribute a u to the 1/2 power inside these parentheses. See, the issue before was that this x is hard to distribute inside of a square root. Okay, it's possible, but it's difficult, okay? And so that x is hard to distribute inside of a square root, but this u to the 1/2 is not hard to distribute inside of this stuff to the first power, right? So this is 1 over 25 times the integral of, and then what is the square root of u times u? Very good. We're going to add the exponents. This is u to the first. The square root is u to the 1/2. So if we add them, we get u to the 3/2, or 1.5, right? Minus, and then the square root of u times 1 will just be u to the 1/2 power, or you could still just call it the square root of u. And now this antiderivative is not so bad. So 1 over 25 times, this is going to be u to the 5/2 times 2 over 5 minus u to the 3/2 times 2 over 3 plus c. Okay. So now I'm going to distribute my 1/25. So 1 times 2 is 2, and on bottom 25 times 5 is 125. What was u? Yeah, u was 5x plus 1 up here, so 5x plus 1 is 5 over 2, or sorry, to the 5 has power, minus, remember, I'm still distributing this 1/25 out front, okay, so don't lose that. This is 2 over, and then on bottom, 25 times 3 makes 75, and then u is 5x plus 1 to the 3 halves power. And then 1/25 times c, it just makes a constant still. And so there we have our antiderivative. Okay? Yeah. So the trick to being able to actually solve that one, right? Yeah, the trick is not to make that one short. The trick is to actually be able to get an answer. Okay? So that is the trick. And I'll just go ahead and tell you right now, on your homework, you need to use that trick on numbers 13 and 14. Okay? So if you want to make that note on your homework, you're going to need to be able to use that trick on numbers 13 and 14. Okay, so 13 and 14 are where you'll use that. Here is your homework, right? Comes off of page 333 and 334 in your textbook. So you're doing 7 through 21 the odd, and then 14 and 22. Again, 13 and 14 are going to require you to use the trick. And the only other note I feel like I should make is that I'm trying to take you up through baby steps, right? So this first section right here is actually, they already tell you what you should be, okay? So they have picked out the you for you already in these. And so all you have to do is use what they've given you in order to go through the process. And then as we go on tomorrow and in the days to come, you'll get better and better at picking out your own you, okay? So you can go ahead and get started on that homework.